Alrighty, hi, this is Mrs. Martinez, and in this video we are looking at the intermediate value theorem. As students, you want to be able to understand and apply this intermediate value theorem. So, to get started, let's talk about what it is. First of all, we can abbreviate it and just say IVT because it is a rather long term and it's going to take you a long time to write. So, intermediate value theorem, IVT. It's an existence theorem, which states that a continuous function on an interval, it cannot skip values because it is continuous. And the IVT states that if these three conditions, which we're about to discuss, if they hold true, then there is at least one number, C, in the interval AB, so that f at the input of C is going to equal K. And here are the conditions. F, first of all, is continuous on the closed interval between the x value A and the x value B. First condition. Has to be continuous on that entire interval. The second condition is that f at A cannot equal f at B in order to be able to use this theorem. And K is going to be a number such that it's going to fall between the output of your function at A and the output of your function at B. Those are our three conditions. Here's kind of a pictorial representation. C is in between the interval A and B. And because your graph is continuous, you're able to find a value, an output, that is between your function at A and your function at B. It is f at C. That would be your K value. This is really a great theorem to use if you're trying to find zeros of a continuous function in an interval. So if your A value, the output is positive, but for your B value it's negative, then there's gotta be a C value that is 0, somewhere between there. So let's get started with our first example here. There's two parts to this. Let's start by asking, is there a value of x, we'll call it C, on the interval, the closed interval, -2, 5, such that the function at C is 1? Well, I'm going to highlight here where the output is 1. It's that horizontal red dotted line. And yeah, we can definitely spot places on our graph where it is an output of 1. But we want to restrict it to the interval, the closed interval, between -2 and 5. And right there, that little blue dot, that is verifying that yes, this does in fact happen. There is a value between -2 and 5 on our graph that is 1. So a C value does exist. But does our theorem guarantee a value of C on that interval such that f at C is 1? Why or why not? Are we trying to use our theorem in an inappropriate example? Well, we have to ask ourselves if it follows through on the three conditions. The first condition, look back at that box, that first page. F is continuous on the interval. Well, is it? No, it is not. You see there is a break. It is not continuous on this interval. So we cannot guarantee this to happen. It did, but we wouldn't be able to use this theorem correctly for this example because it doesn't follow those conditions. Now let's try it for this problem. Is there a value of x equaling c on the interval between 1 and 6 such that the output of your function at c is 3? Okay, so we're looking now at an output of 3, which is where that red dotted line is, and we're restricting it to the value, the input of between 1 and 6. And there is nowhere between 1 and 6 where your graph is 3, so there does not exist a value of c such that your function at c is 3, at least not in that interval. And now let's ask ourselves the question, are we guaranteed a value of c on that interval? No, because the output of f at 1 is 1.5 and the output of f at 6 is -1. So you're not going to be able to find a value between 1.5 and -1 that is 3 by our theorem here. Yeah, it's continuous on that interval, but and yeah, A doesn't equal B, F at A doesn't equal B, but K is not going to be able to fall between F at 1 and F at 6. All right, so the big conditions that we cannot forget and that if we're going to apply our theorem have to be true are that the function is continuous on the interval AB, and that f at c has to fall between your function at A and your function at B. These are the two checks you have to make every single time before you actually determine if you can apply the theorem. So we're going to apply that now, that understanding to this problem. Apply our theorem, if possible, if those two statements are true, on the interval between 0 and 5 so that the function at your c value is 1 for the function y equals x squared plus x minus 1. So we're checking, is it going to be continuous? Well, we're working with a polynomial function. It's quadratic. It's a parabola, and parabolas are continuous on all the reals, so it is for sure continuous between 0 and 5. And then we want to look at those two values, the function at 0 and at 5. At 0, the output is -1, and at 5, the output would be 29. So we're trying to find a value where the output is 1. Well, yeah, definitely that's going to happen because by our theorem, there is going to exist a value c such that if you plug it in, it gives you 1 because the function takes on every value between -1 and 29 on our interval 0, 5. So it will happen, definitely. And if you wanted to check that graphically, you could graph that and actually find that value. But we're going to look now at example 3. All right, we want to use our theorem to show that this function f has a 0 in the interval between 0 and 1. So we're thinking, yes, this is continuous because it is a cubic function. It makes kind of like a really neat little curve, and it's going to be continuous on all the reals, so it's definitely continuous between 0 and 1. And now we're going to look at this interval. Specifically, when you plug in 0, the output is -1. And when you plug in 1, the output is 2. So at 0 it's -1, and at 1 it's 2, and you have to move continuously up from -1 to 2, you're definitely going to go through 0 because f at 0 is less than 0 and f at 1 is greater than 0. So there must exist a value of c such that when you plug it in, it's going to give you 0 by our theorem. All right, last one. Our final example. A car is traveling on a track and it's straight. During the interval 0 to 60 seconds, that's the time, the car's velocity, which is v, measured in feet per second, is a continuous function. The table below shows values for your function. So what we're asked in part A is for the interval beginning at 0 and going up to 60, must there be a time when v at t is -5? Will that happen? Well, what do we ask ourselves? First thing is our function continuous? Yes. Yes, we were told that in the question. Next thing we check to see is can our value of -5 fall between values of outputs that are given? Yes, it sure can, and let me turn your attention right here. On our interval, I'm kind of just concentrating on between 35 and 50 seconds. It goes from -10 to 0. And that means in every second between there, it was increasing from -10 up to 0. So v at 35 was -10 and v at 50 is 0. By our theorem, because this was continuous and you could place that t value between them and get what you needed, which is -5. -5 is between -10 and 0. There is a time when that happens. I'm not sure what time it is, but you would be able to figure that out. It would exist. So ladies and gentlemen, that is all that I have for you in this section. Have a wonderful rest of your day, and I will see you later.